waiting days. And I will screen. That's okay. All right, thank you. Hi, my name is Melinda Wood. I focused my thesis on estimating phenological asynchrony for migratory songbirds of conservation concern in Alaska. Figuring out the mouse here. Oh, no. Mouse. Sorry. Oh, I'm sorry. Okay, I might have to do this one. Thank you. And first, I'm going to start out the presentation with some acknowledgements. I'd like to thank MES faculty John Withy, as well as Julie Hagelin with the Alaska Fish and Game, and April Hardingsker from the Alaska Songbird Institute for their utmost support during this thesis journey. Without them, this would not have been possible. So sorry, for some reason it keeps freezing. What? Oh, no. I don't know if maybe the mouse is. Nope, got it. Yeah, thank you. So research question posed is the amount of phenological asynchrony, so the difference between spring arrival and green up, changing for migratory songbirds in Alaska? So a little background. So phenology, or the timing of life events, is strongly influenced by climate. As some of you know, we've had some declines, about 3 billion birds lost, about 30% since 1970 in North America alone. A lot of it's found with insectivorous migratory birds, but it isn't just restricted to threatened species. So a lot of your common backyard birds like sparrows and warblers are also part of that decline. So birds time their migration a couple different ways. So there's internal cues like endogenous circadian rhythms that can time their migration, as well as environmental cues that can be precipitation, temperature, and greenness that prompt birds to begin migrating. Climate change may be leading to significant changes in synchrony, which can result in negative consequences to their demography. So some species may be able to keep up with these shifts, while others may be more vulnerable. So why Alaska? So during migration, a lot of migratory birds will travel to northern latitudes to achieve the necessary requirements for successful breeding. Alaska sits at about 586,000 square miles. It has unique ecoregions that make Alaska unique. They have large mountain ranges, boreal forests, expansive coastlines, and tundra. And a lot of migratory birds travel to these areas to get abundant resources. About over 5 billion birds will travel to Alaska yearly for spring migration. And northern latitudes are experiencing an acceleration in climate change at an alarming rate, which is leading to concerns about what the cascading effects will be, not only to plant communities, but to arthropod abundance and bird migration timing. So why measure asynchrony? Why is this important? So the timing of brain up is critical to the function of an ecosystem and wildlife survival, and it provides a proxy of food availability for birds. And then as it becomes warmer, spring and vegetation will start to leaf out. Arthropods emerge to feed on these new leaves. And arthropods are a crucial food source to birds. It provides fuel for migration, as well as provides to their young once they start breeding. And then with climate change, with spring warming occurring and green up, it may be occurring earlier or later, depending on the place it's occurring. And these shifts in green up and arthropod emergence can impact the peak availability of food resources during the breeding season. And the concern is that birds may be missing this peak resource availability, which could have fitness consequences on the birds. So how do we measure asynchrony? So ideally, birds will time their migration when the peak resources are available to maximize their fitness. So asynchrony, it just refers to the difference in two measurable phenological events. So for this study, we're looking at the timing of green up and then the timing of spring arrival. And then in a given year and a location, we can then have a standardized way to estimate the timing of green up and the timing of spring arrival for a given species. So for this one, we calculated, this is the difference in days, and the amount of asynchrony for that species in a given year and in that location. And so asynchrony, it can be a positive value when the arrival is after green up, or it can be a negative value if the spring arrival is before green up. So we're looking at if it's changing over time. Is it increasing, is it decreasing, or is it varying, but not with any particular trend? If this does change over time, this could have consequences for birds. So risks of changing asynchrony. So if a bird were to arrive too early, so before these peak resources are available, they risk having colder temperatures. So if they were to start nesting before adequate temperature, their nestlings can freeze. They may risk not having enough resources and decline in breeding success, which is seen as a negative value. If they were arrive too late, so after the peak green-up, they risk having fewer nest sites, competition for mate selection, and less food resources and decline in breeding success, which is seen as a positive value. And it's important to understand these linkages between migratory birds and shifts in climate change to understand our current state of bird populations. So for our data set, we ended up selecting eBird data as our data source. We selected a time span of 2001 to 2022. Originally, we selected 61 land bird species from the 2015 Alaska Wildlife Action Plan. That's the most recent one currently. And then we ended up modifying it to 37 to eliminate any resident species and any with insufficient data. For insufficient data, we set a minimum of 5 years for detections, and they had to have at least a location. And then we sorted data taxonomically using the eBird Clements checklist of birds 2.0. And then we also wanted to sort species by vulnerability scores. So we received this table through the University of Alaska Anchorage. It has status scores for vulnerability. So you can see that the most vulnerable is a red score, and then the least vulnerable is a blue. And since northern latitudes are experiencing acceleration in climate change, researchers have been studying what the cascading effects are. A past study by Mayor et al. Found that around Anchorage, which you can see in the red box there, green-up has not shifted much, but birds were arriving earlier. While in Fairbanks in the blue box, green-up occurred earlier, but birds were arriving later. For our study, we looked into both bird arrival timing and green-up for every year to measure asynchrony and look for changes over time. So for methods and analysis, we ended up taking that eBird data that we received and filtering it through R. We then generated presence and absence tables for each species. And then we were able to use Bayesian logistic generalized additive models, or GAMs, through R to derive our species-specific spring arrival estimates. And then we were able to also receive mid-green-up estimates, which we use through both ArcGIS Pro and R. And then we wanted to set a metric for Julian Day. So we have our beginning start for Julian Day 60 or early March, and then Julian Day 211 or late July. And this just ensures we don't include any species that arrive before or after spring migration. And then to the right, you'll see an example of one species, so what it looks like in GIS for all the detections for 2001 to 2022, and just how dense some of the areas are where detections were seen. And then we also created linear trend tables for spring arrival using Julian Day, and then asynchrony. So this looked at mid-green up minus the spring arrival in days. And then we did model trends over time to indicate which ones were significant or non-significant. And then we generated Pearson's R correlations for each species and hexagon combos with that cutoff of the minimum of 5 years. And then, so for our green up, we ended up getting data derived through USGS Earth data. It's a MODIS remote sensing land cover layer, which you can then later inlay into ArcGIS Pro, and it creates, it uses EVI, which is Enhanced Vegetation Index, to show onset of greenness over time. And it provides a really great layer for looking at phenology metrics. We then were able to create zonal statistics in ArcGIS Pro, and then we ended up generating buffers similar to Young-Flesh et al., where we have 70,000 kilometer squared hexagon buffers for various locations across Alaska. And each hexagon contains a city. And then we later process these in R to calculate asynchrony. And then we had 4 different regions within Alaska selected. So the first one was Southeast Alaska, We did have some good data that showed up in Yukon, Canada, so we did include that as well. And then we had interior Alaska and then South Central Alaska with the surrounding cities there on the left. And then from our green up analysis, we were able to see that there wasn't a directional trend for the 22-year period from 2001 to 2022. So this is an example of spring arrival estimate. So what we were able to generate for each of the species. So for this one, it's for olive-sided flycatcher, which is a species of greatest conservation concern. This is for Anchorage for 2022. So the x-axis is the Julian day, and then plotted along the bottom are also checklists that do not detect olive-sideds by date. The y-axis is the model probability of occurrence, and then plotted along the top, these are the detections of olive-sideds by date, and then the peak of the model fit. This is the maximum occurrence or the greatest probability of olive-sided flycatchers for 2022 in Anchorage. And then we take the half max, which is the half part of the line, with the half with a maximum probability of occurrence. This corresponds to a specific day of the year, so the Julian day on the x-axis, and then we're using this day as a measure of spring arrival for that species in that year and location. And then we take the mean date of olive-sided, and then that would be May 28th. And then we did a comparison of the previous anchors that you just saw, as well as Fairbanks, to see how they would compare. And you can see that Fairbanks is about a week later than Anchorage with a June 6th date, and it does have a wider credible interval. And then we wanted to look at our spring arrival trends. So we generated linear trend tables through R, looking at arrival for each species plus hexagon combos with at least that 5-year minimum. 7 results had trends towards an early arrival. We did have 135 results that had non-significant trends of arrival, with 19 results that had trends towards later arrival. And then we have 2 example plots here, one for Rufous hummingbird and Juneau, and then one for Swainson's thrush and Juneau. And then you can see that Rufous hummingbird had a negative trend, with Swainson's thrush having a positive trend, both with a 90% confidence interval. We then wanted to calculate asynchrony, so that date of spring arrival plus the date of mid-green up. And then you can see that the closer the blue is to the green dot here, less asynchrony, and then the wider the span is between the green up and then the arrival is our level of asynchrony. And then so for asynchrony, we ended up taking the species and hexagon combos with at least the 5 years arrival and calculated it with a linear trend. We had 10 results that had trends toward decreasing asynchrony. We had 136 results with non-significant trends of asynchrony, 14 results that had trends toward increasing asynchrony. And then we had 2 examples here, one of Rufous hummingbird and then one of Wilson's warbler. You can see that Rufous hummingbird had a positive trend in asynchrony, while Wilson's warbler had a negative trend in asynchrony. Both are level 2 red on the final ranking score of vulnerability. And then we have that same Swainson's thrush from Juneau from the last slide, and we wanted to compare it to another result we got of a Swainson's thrush from a nearby neighboring hexagon in Haines, Alaska. And we can see that the trend started close to 0 or earlier, and then asynchrony did not increase significantly. We found that for this species, there was not a trend of poor asynchrony, but with the 2 hexes side by side, it showed the opposite trend. And then we wanted to see if there was any evidence of species tracking change. So are they able to keep up with the changes in green up over time from year to year? So we looked at both mid-green up and spring arrival, and then we calculated anomalies from each year. So this line represents the long-term average in mid-green up. And then, for example, if we look at the level of 2016, we can see that this value is way below the green line. So it's an earlier green up than the long-term average. Then we did the same thing for spring arrival. And for a given species and location, we did a correlation test of the arrival anomalies. And we use this to see if birds are tracking variation in mid-green up. And then with the results, we were able to find that 31 correlations had a positive result. This indicates that these species might be tracking changes in green up. And then 21 of the 37 species did not have a positive correlation, and with 133 correlations being non-significant. And then 2 species had a negative correlation. And then 23 species total, 23 of those species total may not be tracking changes in green up. So the negative correlation is evidence that that it is an earlier than normal green up year, that there may be an earlier than normal arrival. And then if it's a non-significant correlation, it could also indicate that those species may not be tracking as well. And you can see on the chart here that we have the species that may be tracking changes in green up with each location, and then the 2 species that may not be tracking changes in green up. And then we have the same species with a chart added with the status scores there at the bottom. So the species that are tracking changes here on the right, and then the 2 species that may not be tracking changes, you can see that both have negative correlations and are also both considered vulnerable species with status score of orange and red. And these may need more conservation action for those 2. And then in conclusion, we were able to see that arrival estimates pinpointed which species may be arriving earlier or later than average. The Pearson's R correlations highlighted which species may or may not be tracking changes in grain up. And since the EBER data is fairly limiting, we had certain areas that we just weren't able to include because they didn't meet that threshold of 5 detections or more. So for future analysis, we could increase spring arrival detection with maybe including historic banding data. And then since there is possible fitness consequences both in breeding and nest success in Alaska, this research can help inform wildlife conservation management for species of greatest conservation need. Thank you.